So let's consider what would happen if you were to hang a heavy object on the end of an aluminum. So let's say this is aluminum and this is lead, and you have a lead object or lead sphere hanging on the end of an aluminum wire. Okay, and let's say the aluminum wire has a length of 2.25 meters. Okay, let's say that the lead sphere has a radius of 8.25 centimeters. And I want to know what's the minimum diameter aluminum wire necessary in order to keep this thing from crashing down. So I want to know the minimum diameter wire. Okay. All right. So you look at it and say, well, what do we do? Well, minimum diameter wire, I don't want it to come crashing down. I don't want it to break. So that means I'm looking at the ultimate strength of aluminum. So we need to look up on a table somewhere the ultimate strength of aluminum. So for aluminum, the ultimate strength turns out to be 110 times 10 to the 6 Newton per meter squared. Okay. Now, we know that the ultimate strength is a measure of stress, so that's M over A. And so that's going to be equal to mg over pi r squared. Now, what are we talking about? The r is not the radius of the object. The r is the cross-sectional radius of the wire. So double that gives the diameter of the wire. That's what I'm after. And so this is what we need. So we've got SAU, we got G, we got pi. So all that we need to do to solve for R is we need to find the mass of the heavy object. Well, that's easy. The mass of the heavy object is going to be the density of lead times the volume. Well, it's a sphere, and so we know that for a sphere, the volume is 4/3 pi r cubed. So all we need is the density of lead. And so we look that up. Density of lead is 11.3 grams per cubic centimeters. If we convert that into SI units, that's going to be 11,300 kilograms per meter cubed. Remember, 11.3 gram per centimeter cubed. Okay, so we know that a kilogram is 1,000 grams. Okay, and we know that 100 centimeters is 1 meter, and we got to cube that. And so that gives us 11,300 kilogram per meter cubed. So we plug that number in up here for mass. And so the mass would be 11,300 kilogram per meter cubed times 4/3 times pi times the radius, which is going to be 0.0825 meters cubed. And so the mass comes out to be 26.6 kilograms. Okay, so now we know that SU is F over A, so that's mg over pi r squared. So R is going to be the square root of mg over pi SU. So that would be the square root of 26.6 kilograms times 9.81 meter per second squared divided by pi times 110 times 10 to the 6 Newton per meter squared. So R is going to be equal to 8.69 times 10 to the minus 4 meters. Okay, so 8.69 times 10 to the minus 4. If you multiply that by 2, so the diameter is 2r, that comes out to be 1.74 millimeters. Okay. All right. So let's explain this problem a little bit. Let's say we have this object here. Okay. So we have the mass, same object. Okay. So it's got 26.6 kilograms. And I'm going to hang it from a wire, but I don't want the minimum thickness wire. I want the wire to have a radius that is about 25% larger than the minimum radius. In other words, I want to make sure I hold this thing. Okay. And so let's say that L is 2.25 meters. So that means that R is going to be 1.25 times the 8.69 times 10 to the minus 4 meters. So R is going to be 1.09 times 10 to the minus 3 meters. Okay, so that means that effectively we got a 2.2 millimeter diameter wire. So 2.2 millimeter diameter wire. It's a pretty heavy wire. And so what I want to do is I now want to know how much does it stretch. What is delta L? Okay. So we know that stress is modulus times strain. Okay. So easy. Delta L is going to be F L naught over A E. Okay, so F is mg times L naught. A is pi r squared E. Okay, now, the R is this R right there. It is not the radius of the object down there. I once had a person do that. Or I actually once had a person try to find the surface area of that thing down there. No, it is the cross-sectional area right here. That's the pi r squared. Okay, so we look at this and we have everything we need, except we need to know the Young's modulus for aluminum. So that's another thing we have to look up. So that's 70 times 10 to the 9 Newton per meter squared. So now we just plug in all our numbers. So delta L is going to be mg L naught divided by pi r squared E. So delta L will be the 26.6 kilograms times 9.81 meter per second squared times 2.25 meters divided by pi, 1.09 times 10 to the minus 3 meters squared. And then the E was 70 times 10 to the 9 Newton per meter squared. So delta L comes out to be 2.25, or we'll round it 2.2 times 10 to the minus 3 meters. So in other words, it's 2.25 centimeters long, but it stretches about 2.2 millimeters. That's 2.25 meters long, stretches about 2 millimeters.